The solution of a linear system, or a system of equations that we've been talking about, is a set of numbers that satisfies each equation in the system. And I have 3 options for the solution. I can have one solution, I can have an infinite number of solutions, or I can have no solution. If I have one or infinite, then I have what's called a consistent system, and if I have no solution, I have an inconsistent system. So some vocabulary for you to know. Consistent means it has at least one solution. Inconsistent means it has no solution. And these are my 3 essentially examples of my 3 options graphically. So if I have a consistent system with one solution, in 2 dimensions, it looks like this, as if I have 2 independent lines, they're not related to each other, and there's one intersection point. For example, if I have a system that looks like this, 3x plus y equals 5, and then x minus 3y equals 7. Those are 2 independent equations that give me one solution. As a vector, it looks like this. This would be my x vector, this would be my y vector, and this is my b vector. If I have a consistent system with an infinite number of solutions, it looks like this graphically, where I have 2 parallel lines. For example, it would look like this, 3x plus y equals 5, or 6x plus 2y equals 10. It's just the same information twice. This is the same line. I just multiplied this equation by 2. So this is an example where I might have a consistent system with an infinite number of solutions where I just have 2 equations with the same information. And if I look at my vectors, all of these vectors essentially lie on the same line. 3, 6, 1, 2, it's the same vector twice, one's just scaled by 3, and 5, 10, scaled by 5. So they're all on the same line. The third example, or the third option I have, is an inconsistent system with no solution. And it looks like this, where I have 2 parallel lines, where there's never going to be any overlap. And this occurs when I have conflicting information. So if I have 3x plus y equals 5 and 3x plus y equals 10, that's just not possible. I'm not going to find a set of x and y values that give me a 5 and a 10 at the same time. So I have conflicting information. So for this one, this first set over here, I have what's called independent. They are called linearly independent lines. This one I have dependent lines. It's the same information twice. And this one I have conflicting information. And this just explains our observations here. Where here is non-parallel lines, and they're not collinear, which means they're not on the same line. Here is parallel lines and collinear with my b vector here. And then here is parallel and collinear, but this here is separate. This is my b vector. I forgot to mention my vectors over here. So x and y are together, they make sense, but then my b vector is not at all on that line. It doesn't coincide with my equations at all, or my vectors at all. So this idea of our lines needing to be linearly independent in order for them to have one solution leads us to this idea of what's called linear dependence. So a vector u is set to be linearly dependent on another vector if each of them is a constant multiple of the other. This is where we see linear combinations come into play again. So here's some mathematical notation, but essentially I'll just talk about how we apply this. So the set of vectors in Rn, I forgot to mention this at the beginning because we took a week off, but just briefly, Rn is the space that a vector lives in, where n is the number of elements. So if I have a vector with 2 elements, 3, 2, it lives in your 2D space, or R2. If you have 3 elements, 3, 4, 5, this is a 3D space, or R3. If you have 4 elements, it's R4 or a 4D space, etc. That's what Rn means. Brief review, not review, but brief introduction. So a set of vectors in a given space, in a 2D space, a 3D space, whatever, is considered linearly independent if the only solution to our linear combination is the trivial solution. If all of our coefficients, all of our constants here end up being 0. So if you want to determine, one of the ways we can determine if a set of vectors is linearly independent is set of our vectors as a linear combination. So C1, V1 plus C2, V2 plus C3, V3 equals V4. And we're going to solve for our constants. So C1, C2, C3. Essentially, it's V1x plus V2y plus V3z equals V4, or equals our B vector. It's just a system of equations where we're solving for x, y, z, or C1, C2, C3. If it ends up where all of our constants, all of our solution is just 0, if x, y, z in this instance equals 0, if C1, C2, and C3 equals 0, then our vectors are linearly independent. If we end up with some that are not 0, then they are linearly dependent. So we'll look at examples of that. But it's really just solving things just the same way you have. It's just the way we're interpreting our solution.